the bane of neuroscience has been that most methods record from the cell body. And so I think we're all somatocentric, I like to say, which means that we all think that the spike at the cell body is somehow more meaningful than anything else that happens in the neuron. And I think from a computational point of view, it's the least interesting part of the neuron. The question is, if having just seen a movie and somebody recorded all your action potentials, if they replayed all the action potentials very faithfully at every neuron in your brain, would you have the experience of seeing the movie again?
This is Brain Inspired.
Welcome to Brain Inspired. I'm Paul. Are dendrites conceptually useful? That's the title of a recent perspective piece from Matthew Larkum, whose voice you just heard. Matthew runs his lab at Humboldt University of Berlin, where his group studies how dendrites contribute to computations within and across layers of the neocortex. Over the past few years, Matthew has published many theoretical proposals and many experimental results that argue for a better appreciation of the role of dendrites in our cognition, like perception, memory, consciousness. All of these ideas fall out from the unique structure of pyramidal neurons in our cortex. Pyramidal neurons are the majority of the neurons in our cortex, and although we name them by where their cell bodies are in the cortical layers, like layer 5 pyramidal neurons or layer 2-3 pyramidal neurons, Matthew argues it's more useful to consider which layers their dendrites occupy, because their dendritic trees stretch out in different directions to receive incoming signals from different areas of the brain. For example, layer 5 pyramidal neurons have a set of dendrites at their base, which receives mostly feed-forward projections from earlier brain areas, and by earlier I mean closer to sensory areas. So as early visual cortex projects forward, those projections land on the basal dendrites of the later area. Those same layer 5 pyramidal neurons have dendrites that project up into layer 1 of the cortex, called apical dendrites, and those dendrites largely receive feedback projections from later brain areas. That's simplistic, of course, because there are other lateral projections and connections across layers of the cortex and so on. But the story remains that these two sets of dendrites from the same neuron are receiving signals from fundamentally different brain areas. One of Matthew's early key findings was that these two sets of dendrites are electrically separated, and depending on what's receiving signals at any given time, the neuron will either be silent, if only the apical dendrites are receiving signal, or will fire at low levels if only the basal dendrites are receiving signal, or fire in a bursting mode if both are simultaneously receiving signal. This led Matthew to realize this coincidence detection type mechanism makes for a great way to associate feed-forward sensory-like information with feedback, memory, or context-like information, and might therefore be a fundamental principle of how the cortex operates, a big question in neuroscience. So we discuss a handful of the ideas and experiments that fall out from that, like I said, related to learning and memory and consciousness and more. We also discuss how Matthew's work has made him appreciate how a bottom-up approach, or examining the implementation level in terms of Marr's famous levels of analysis, can inform what algorithms and computations might be possible, as opposed to starting with the computation and figuring out how it must work in the brain. We talk about how the principles derived from dendritic computation might improve deep learning. You may remember many episodes ago, I had Blake Richards on, that was episode 9, and Blake used Matthew's work as inspiration for his neural network models to solve backpropagation in the brain, for example. And toward the end, we discuss a recent thought experiment Matthew and a couple of colleagues offered, asking whether action potentials, or more broadly brain activities, cause consciousness. Oh, and there are a few guest questions from Mac Shine, a previous guest on episode 121. Okay, sorry for the long intro, but I thought it would be useful to set up the background a little, even though we cover it in more detail in the episode. Find links to Matthew's lab and the papers we discuss in the show notes at braininspired.co/podcast/138. If you find value in this podcast, consider supporting it for just a few bucks through Patreon. Or if you want to dive deeper and learn more about the conceptual foundations of a lot of what's discussed on the Brain Inspired podcast, consider taking my Neuro AI course, which you can learn more about at braininspired.co. All right, here's to the Dendrite, and enjoy Matthew. Matthew, pleasure to have you on. Thanks for being here.
It's wonderful to be here. I've really enjoyed the podcast. It's been, for me, a revelation. My PhD student put me onto it, I think around about the time you interviewed Georgi Buzaki. And since then, I've just faithfully listened to it nearly every week.
Oh, that's so funny that...
for me, it's a fantastic thing.
Oh, well, thanks for saying that. It's funny that I hear that quite often, that someone's PhD student put them onto it, just as you said. So I guess it's working in that respect. I was trying to figure out how to describe what it is that you do. And one way to describe that would be that you are wreaking havoc on the notion, the primacy of the neuron cell body and the action potentials produced there, and championing the role of dendrites. That's a very simplistic way to say it, but how would you say it?
Oh, I'm glad you put it like that, actually, because I would like that message to come across. I don't know where to start in the trajectory of explaining why or how you could come to that opinion. Well, from a historical point of view, from a methodological point of view, I think that the bane of neuroscience has been that most methods record from the cell body. And so if you think of like a extracellular recording, it'll pick up spikes that are near the tip of the electrode. And if you do a targeted whole cell patch recording or even a juxtacellular patch, or if you use other methods like calcium imaging, which is now one of the main methods in neuroscience, they all are much better at picking up signals from cell bodies. And so I think we're all somatocentric, I like to say, which means that we all think that the spike at the cell body is somehow more meaningful than anything else that happens in the neuron. And I think from a computational point of view, it's the least interesting part of the neuron. And I think that, if you would do this exercise, if you would collapse all of the branch points in a neuron, including the cell body, and you'd make them all just tiny nodes, right? So there's no big sack of lipid which represents the cell body anymore, but just little junctions where things meet. Obviously now your electrodes would not think the cell body is special in any way. The axon is where you could say the output is, and it's also where the output is generated, which happens to come out of the somatic node, but who'd know that if it was as small as every other junction point in the neuron? And now you would be saying that this entity, the collapsed neuron, would be transforming inputs that come everywhere, more or less everywhere else but the cell body, not completely, but to a first approximation, and transforms it in the axon to outputs that also go all over the place. You'd never mention the cell body, and yet this is the place that is central to describing a neuron and to describing the computations that neurons make. So I think in the first instance, it's almost irrelevant.
Well, I know that I've heard you talk about how Ramon y Cajal appreciated the role the potential role of dendrites. And in his beautiful drawings, it's interesting. I don't know if in neuroscience it's still taught with the sort of cell body as the primary focus. But when you look at his drawings, of course, there are all these different beautiful structures of dendrites and axons. And you've quoted him in some of his work appreciating and sort of speculating that there might be a computational kind of role for those dendrites. So do you know, is it still taught that, I don't know if you teach neuroscience
I do. Yeah.
Well, I know that I'm sure the way that you teach sort of diminishes the role of the cell body, but I guess writ large in textbooks, it's still somatocentric, as you said.
That's right. I start with when I get to this subject, I start with a slide showing about 10 different pictures from textbooks, and they typically, almost all of them have a sizable cell body, looks like an orange or something, and it's got tiny little sort of hairs coming out of it, which are the dendrites, but they're really de-emphasized. And then if you're lucky, it's got one myelinated axon coming out, and then a sort of hand structure at the end, which represents what could be the processes of the axon. And basically the dendrites, you could forget them if you didn't look carefully in the textbook. And yeah, I guess I complain usually in my lecture that this is my favorite subject and the dendrites are missing, but there's usually a few tittles, and then we get on with just describing the way you have to, basically, the way a neuron operates. At least if we're talking about basic neuroscience. If I get high level course, then I get the chance then to do all my propaganda on what I think the neurons are really doing.
So you're just disgruntled for a few moments there and then move on, huh? So
yeah.
We were talking before I hit record that the arc of the story of your research is quite long, and I'm afraid that we're not going to be able to get to a lot of the things. Maybe we could start, I'd like to start before 1999, but a lot of when you start, often I think that you send people the 1999 paper in which you're recording, apical dendrites and from the basal dendrites as well. So maybe we could start just what the dendrite hypothesis is, and then I would love to hear how you came about searching for these sorts of questions, doing these experiments and asking these questions.
I think it's going to work better the other way around, because the only way the dendrite hypothesis makes sense in my mind is to step back and look at the cortex the way I came to look. Yes, right. The way I came to look at the cortex, first of all. Actually, in the end, we're I think more recently, at least in my lab, exploring the way the cortex interacts with subcortical structures, and so it's perhaps a bit rash to just say cortex, but nevertheless, I think it's quintessentially a hypothesis about the cortex.
Is that how you began thinking about it, or is that where the recordings and experiments came from, is thinking about cortex and the multi-layered structure, etc.?
Right, absolutely. So I found myself in a laboratory, it was Bert Sackmann's laboratory in Heidelberg, which I arrived at in 1997 as my first postdoc. And so this is the guy who's invented patch clamp and won the Nobel Prize for it. And by that point, the lab was humming with they'd had almost a decade at this point of fabulous findings on after being able to patch dendrites for the first time at the same time that they could record from the cell body. So basically do the first experiments into how signals were generated in the dendrites and how they propagated around the neurons. So I came into sort of a second generation of researchers looking at this after the first amazing, revolutionary experiments that had been done. And back then we took slices of cortex from rats. Mm-hmm. And so my first confrontation with the whole thing was to look at the cortex side on in the dish, as it were, under a high-powered microscope. And what you see in that situation is mostly pyramidal neurons. And if you've done a nice preparation, you see their dendrites quite nicely. And so what you're effectively looking at is a forest, of tall trees, and where the cell bodies have roots going down, and they all oriented the same way, like a forest, and then there are tough dendrites at the top. And I don't think you can look at that structure and not ask, why the hell is the cortex made of these really peculiar but specialized neurons? And I think it's natural to, and Cajal, as you mentioned, also did the same thing. He looked at these neurons and said, whoa, there's got to be something special about these neurons. But by then we were finding out that not only were they morphologically special, but physiologically or biophysically. So they have a whole complement of specialized channels that are distributed in specialized ways that make this a much more complex machine than the sort of neurons you find to this day in either models of the cortex or models or artificial neural networks and so on. So they're just obviously, on their face, much more complex. But of course, you don't know a priori what this complexity serves and what it's doing. So when I got to the lab, the talk of the town was the latest recordings and publications of Jackie Schiller and Greg Stewart that had shown that there was not just a spike in the axon, but there was a special dendritic spike. We subsequently found there were more than one type, but at the time there was a so-called calcium spike, or sometimes called a calcium plateau potential, right at the top of this tree. You can think of it like a big oak tree or something. There's right at just before the branching out into the tufts. There's another zone, an initiation zone for an incredible spike that's more like the spike you get in heart muscle, and it's actually due to the same channels. It's the long-lasting calcium channels that sustain a plateau in this dendrite. So it's altogether more amazing and incredible than the spike that we all know and love that comes out of the axon, the so-called sodium spike. And at the time, people, in particular, Sackman, I think, was the boss, as it were, was skeptical about whether or not the calcium spike would be of any use because it had a high threshold, and it was difficult to imagine what would actually make it fire. And so it wasn't completely clear whether it was just an artifact or an anecdotal,
byproduct,
if you like. Byproduct, yeah. And I remember I was trying to explain to my wife, who, as I say, is a musician, and so it takes some time to get through these nutty details. And I had to explain to her on a long walk once what I was doing and what the point of this calcium spike was, and the other point that had been discovered just before that was that the sodium spike that everyone knew went down the axon and signaled the next neuron also went back up the big trunk of the tree, and
also a byproduct, right? That's the idea.
Maybe, yes, right. And people were speculating what the good of that was, and so it all hit me in an instant that it could be that the signal that's generated at the bottom of the tree basically primes the top of the tree such that you can reach threshold for inputs coming into effectively the leaves at the top, the dendritic tufts. That
idea just came to you of a sudden?
Yes, it was a sort of eureka moment on a Sunday as we were walking through the forest in Heidelberg, and I by Monday afternoon I had the first result, which was that indeed this is the case, and it's even more exciting that because what it does is halve the threshold for the big plateau potential, the calcium spike in the dendrites. And that in itself leads to a kind of ping pong exchange between the top of the neuron and the bottom of the neuron that causes it to burst fire. And so effectively you can arrange it such that innocuous inputs that appear to be doing nothing on their own make the whole neuron explode. And all of a sudden I think it was clear to me that this was an associative device. The neuron was basically associating whatever came to the top and the bottom of the neuron. So the next question was, what goes to the top and the bottom of the neuron?
Right.
And to some extent, we're still trying to work that out. But I think in broad strokes, to a first approximation, you can say that the top of the neuron receives a lot of long range input that's predominantly feedback in some hierarchical sense, meaning that if you've got something coming from a higher, let's say you said secondary visual cortex or seminosensory cortex going to primary cortex, it'll target the top of the cortex, and higher order thalamus targets the top of the cortex. And lots of the superior colliculus targets the top of the cortex. We've now subsequently learned that lots of memory structures target the top of the cortex. And in the event that if you saw that architecture in the first instance without knowing about this physiological property, you'd have to wonder what the hell it's doing going to the top of this tree particularly when you do the actual electrical recordings and you find that it has no influence at the cell body. It's basically a flat line. If you put in input at the top of the tree, there's basically nothing to see at the bottom of the neuron.
And that's because of it's electrically decoupled essentially because of the long dendritic tree structure.
That's right. I mean, this word decouple comes into the picture right in the most recent stories that we've had, because it seems that it turns out, and this is jumping right to the end now, that the brain has a handy little switch to couple the top to the bottom of the neuron. And that means that it's possible, given that I should have completed the story and said that we think the bottom is receiving predominantly feed forward, although, let's just leave it in simplistic terms for the moment. There's complexity in everything and exceptions to everything.
No.
But to a first approximation, you've got a feed forward drive to the bottom and feed back to the top. And if you would have the neuron decoupled, such that the top can't influence the bottom, then you've basically taken feedback out of the system with one fell swoop. And that's what the cortex has as a handy switch, and something that would be fantastic to try out in a model. And I guess it's too early at this point because that's a fairly recent discovery. But in the dish, so in vitro, they tend to be decoupled. And when you put them in vivo in the awake state with neuromodulation and so on, they tend to be coupled. But coupled here is, so the way this term coupled is going to be confusing at this point of the story, because it's still the case that the bottoms can signal the top and cause a kind of cooperative interaction between the two regions. And that, I think, is still a fundamental way of explaining what the purpose of the cortex is and what it does, which may sound like a bold claim, but I'd have to deconstruct that claim to try to convince anyone that that's the case. But now I'm completely convinced at this point that the key to understanding the cortex is understanding this neuron and the architecture of long-range connectivity.
But so this neuron is a layer 5 pyramidal neuron, and the cortex is made up of multiple layers. Why this neuron? Because there are other layers that, of course, stretch out among other layers in the column, stretch their dendrites and axons out, and of course have lateral connections. So why the specific? Because I know that you're also looking at layer 2, 3 pyramidal neurons, which also have that kind of structure. But why the layer 5?
Yeah, I would, in the first instance, I'd say it's the pyramidal neuronal type that should be used with this description. They're all subtly different from each other. The main point being what we call the layer 5 neuron is the neuron with the cell body in the soma, which, by the way, is if my claim is right that the cell body is not relevant, then there's nothing layer 5 about this neuron in particular. But
no, let's pause there, because you kind of reformulate that. That's kind of the way that we think of traditionally the cortex, or the way I was taught is in layer 5 there are the cell bodies of the pyramidal neurons, but you're kind of reformulating a perspective on how to think about the cortex, because all of the action taking place is essentially outside of the layer. Well, a lot of it is outside of the layer in which the cell body exists. So
that's right. Yeah.
Maybe, I don't know, can you elaborate on how your perspective on the cortex differs then?
Sure. So I mean, I think in terms of describing what a neuron does, I think the easiest thing to say is that it's transforming inputs into outputs. That's probably maybe too boring, but if that's the case, then you have to look at where the inputs are and where the outputs are. And maybe the last thing you want to ask is where is the transformation happening, and which could be everywhere. I'm claiming that the last place you want to look is the cell body for this transformation, but in principle, the transformation starts where the inputs arrive and involves the entire neuron in terms of, because signals are going up and down, back and forth, and causing different kinds of signals in different places, in a very, very complex way, and none of which has anything really to do with where the cell body happens to be. And then in the end, the axon itself typically goes all over the place, and you can't easily predict which layer, or even whether or not the output remains in the cortex. So actually, there's no particular layer that this element, the neuron, is confined to. If you ask yourself what is the function of this neuron, you're going to have to essentially find out what are all of the interactions that can occur within the dendritic tree, mostly within the dendritic tree. In principle, there's some things that could happen in the axon. And then you're going to have to describe this in terms of the long range, so where the inputs to the cortex arrive and what they represent, what kinds of, what classes of information this represents.
You know, I realize we're talking about on a smaller scale than when people usually formulate hypotheses about what the cortex is doing, right? They talk about the cortical column and as if it's a unit operation. And then there are different, high level theories about what each column is doing. And then that's repeated over all of the different columns essentially, and just specialized based on where the column is. So is your idea it's less about the cortical column so much, or maybe you can correct me. I'm trying to think of like how your ideas fit within the, higher theories of cortex, so to speak.
Yeah.
Because we're talking about a very specific kind of cell structure and the way that it is decoupled and or coupled depending on which kinds of inputs. And I'm kind of jumping the gun here, I know, but
I think it fits well into the view of the cortex's, the sort of Mountcastle view that there are lots of vertically oriented columns that basically are all, dare I say, feature encoders or detectors, and very much with a kind of hierarchical view of that, such that some of these cortical columns are receiving more primary information. That means in the stream of information from the outside world to the inside world, they're early on. And then there are other cortical columns that are higher up in that hierarchy, meaning further along the processing line. And then with lots of information going in the other direction. And so in that scheme of things, if we just stick to primary sensory cortex for a minute, then you would be claiming that that the role of the pyramidal neurons in this sense, first of all, the layer 5 pyramidal neuron is the only neuron that spans all of the layers, so it collects input from all of the layers, and it's the only neuron that goes completely out of the cortex, with the exception of some layer 6 that also go to the thalamus. But the layer 5 is an output neuron in the sense that it's projecting both within the cortex long range, but also outside the cortex very long range. They're the neurons, for instance, that would go to your spinal cord and directly synapse onto motor neurons. So that there's some kind of encapsulation, if you like, of what the column is doing. You'd like to think anyway. It's hard to imagine that's not the case. And so I presume that the circuit of a column at a minimum is serving to encapsulate some feature that's either in sensory space or at high levels are some more complex features, and that if you would record from the layer 5 neuron, you'll have the best idea of what the brain or cortex currently thinks is a feature in cognitive space, let's say. And in that world, if that's a good way of looking at the cortex, I think there are categorically two kinds of information, at least, and two really important types of information. One would be the feed forward stream, which would represent the information coming from the external world, and one would be the feedback stream, which would represent information that's been generated in the cortex itself. And it would make sense of why you want to have neurons which are elongated and have a large set of dendrites collecting inputs at both ends. And essentially at least two compartments, you can imagine two boxes or or two neurons, in fact, at both ends. And that one is predominantly collecting one kind of information, and the other is predominantly collecting the other kind of information. And in fact, since these are very difficult words to use, feedback forward, feed forward, or top down, bottom up, and typically this is the stumbling block for many conversations. You could just take the attitude, why not talk about a basal and an apical being the description of the top of this neuron, and basal being the bottom of the neuron. And then we could worry about what terms we want to use later on for this. But essentially you could say this neuron is allowing you, first of all, to separate those two streams of information and then bring them together in special ways under special conditions, and have a way to manipulate those conditions and the way you combine them.
Well, yeah, I was going to ask, because it's kind of easy to wrap your head around it when you're talking about, let's say, early visual cortex, right? And where you're having most purely sensory data coming in, and you're looking at features of a tiger or something. I think you often use a tiger in your examples. And then so that's coming into the basal dendrites, and then all these, and again, I'm jumping the gun, but these, I'm going to say feedback connections coming into the apical dendrites, which are, memories of tigers and models that the brain has built, etc. Context is what you refer to. Mm-hmm. So it's kind of easy to think about it like that. But then as soon as you go up another hierarchical layer, that feed forward information is not sensory anymore, or it's less sensory. But now it's still feed forward, right? But then it's like the sensory information that's been transformed by the context and memories, and we'll talk maybe about memories in a little bit. So then it's, like you said, those are tricky terms, feed forward and feedback, but all of a sudden you're already in a very kind of complex model as opposed to like the simple sensory versus feedback story.
I agree, but I think that's the beauty of it. I mean, the point would be that what is context for one region could be data for the next, and vice versa, and this will depend on where you are in the processing. But it could easily be that that means that this is loops upon loops in some sense, and that although there would be a way to describe, let's say, a direction of flow of information, in the end, this is all going to be very much, this is going to get very complicated very soon in terms of how you would describe what any given column that's not at the top or the bottom is actually doing. I think the other thing that maybe is occurring to you and occurs to most people is that what happens at the top, because it turns out that the other thing to say, which I should have started with really, is that the whole cortex is full of these neurons. They're ubiquitously everywhere. And they're not in other structures. They're like 70 to 80% of the cortex, and you don't find them elsewhere. So there's something special about this neuron for sure. And they're ubiquitous throughout the cortex, and you find them at the top of the so-called hierarchy just as much as you find them at the bottom. And with this simplistic way of describing it in terms of feed forward, feedback, what's feeding back to the apical tufts of neurons at the top of this hierarchy, you might ask.
Right. I was drawing this out, and I have a big question mark right there in my diagram.
Right. I think when we get to this point, that's where I think the words fail us, and where the language is really just a hindrance. What I'd rather say is that we've got that the cortical column is architecturally speaking, at least from the point of the neurons and the 6 layers and so on, is more or less the same at the top of the hierarchy as it is at the bottom of the hierarchy. And I presume, we know that the properties of these neurons are, if not identical, roughly the same. And so we do know that inputs coming to the top of neurons in prefrontal cortex, is doing roughly the same as inputs to the top of neurons in sensory cortex. So that's where I say it'd probably be better to reframe what a cortical column does with respect to the top and the bottom of these neurons, which ends up being particular layers, rather than trying to find an English word to describe the information categorically such that it's always the same.
There's probably a good German word for it, no?
Probably, yeah. No, well, actually, when it comes to these words, I think they use the English. I'm just trying to think whether there's a specialized German word for feedback and feedforward.
Don't they just stick words together? And
yes, they do. Yes,
neologisms,
yeah. We could probably definitely. Yeah. In any case, I think the fact that it's the same everywhere is, in a sense, the guiding principle for claiming that there's something special about this neuron, about what it's actually doing in the first place. And then you can ask yourself, well, I mean, essentially what the word you brought up, the word context, which is the best word I think one can find as a best English word, I think, to describe what might be coming to the top. In other words, if you imagine that the output of this neuron is encoding some either low level or high level feature, that a feature is everything that you're trying to encapsulate and propagate. And context is everything other than that relates to it. So if you're talking about the tiger, for instance, which is what I always go back to, then if you're talking about the color orange, you might want to associate, so you're the orange column, let's say, or let's say you're talking about the neuron that is giving information about whether or not orange is in your cognitive space. Then other things that are not orange, but relate to orange, particularly in the case of a tiger, can then be linked, if you like. And if you asked where are they linked, I would say they're linked at the top of the neuron. The top of the neuron can get other things that tend to happen when orange is in your cognitive space. If you ever think about tigers, then you'll have learnt to associate stripes and growls and movement and anything else that pertains to that. And I would expect to be finding that kind of information affects the top of the orange column in your brain. And then if we now transfer that to higher cortical areas, it's still the same operation. So especially doing some complex decision, there'll be some output that relates to the decision and the type of decision you're trying to make and so on. And there'll be other things that often occur during that decision that are not the decision itself that you could call context, that come to the top of that neuron.
Is this a good time, do you think, to talk about consciousness and the dendritic integration theory? Because we're talking about, you've used the word feature, right? Where each that's what gets passed along. But then when we think of our experiences, coupling the features or the input with the context, and then a feature is passed along, and that's happening at every hierarchical level. And as we just said, there's a big question mark about the top and how it's the wrong way to think about it. But one of the things that you guys have found is that under anesthesia, it's decoupled. The pyramidal neuron is decoupled, and when we're awake in a conscious state, it's coupled. So, however, if we're in a conscious state, the coupling would be, all over the cortex, right? Everything is potentially at least coupled. So then you immediately think, well, how does this? Well, maybe you can explain what the dendritic integration theory is, and then maybe we could discuss like how to wrap our heads around where our experience arises, essentially. I know that this is terrible. It's a podcast, and we have to use language, and language is no good. Right.
But I ought to be able to do this. I'm glad you started with the anesthesia, because I think in a way we don't. It's a very nascent theory of consciousness. I think it's more a theory of loss of consciousness at the moment, and it's giving us hopefully some information about consciousness, and the sense in which we're proposing a theory of consciousness, not so much that we think we've solved consciousness, but we're looking at the other leading theories of consciousness and saying, how does this mechanism that we found that clearly is at least correlated to loss of consciousness, if not the mechanism for the loss of consciousness, what that actually informs us and how that relates to the leading theories of consciousness. So yes, it's as you say, if you record from these the cell body or so close to the axon of a layer 5 neuron in an awake, in this case mouse, and you optogenetically depolarize or excite the top of the neuron, you see what we see under many situations in vitro, where the top signals to the bottom and causes it to burst fire, as I was saying before, and this is very clear to see. And then if you anesthetize the animal with different kinds of anesthetics, you find that it flatlines. That although you continue to excite the top, because we're basically imposing that optogenetically. That's to say, we express channel rhodopsin in the neurons and put light specifically on the top of the neuron. Then under the anesthesia, you get no effect at all in terms of cell firing of this neuron. And well, that was for me astonishing in the first instance, because I mean, you might think, well, anesthetics are anyway subduing the network and so on, and so maybe you should expect that. But this is a biophysical claim, because we're taking single neurons and we're forcing depolarization at the top of the neuron. And we're saying that depolarization is not doing what it did just a minute ago. It's not getting to the bottom of the neuron. So it's a biophysical claim about the neurons. Of course, we do think that circuit elements are impinging on that neuron and preventing the coupling from the top to the bottom. But what in that instant, what we could see is that, well, after a few more experiments, maybe I should say, because let me just flesh that out. It's completely we also found that if you suppress the higher order thalamus that projects to that particular region that you're recording from, that has the same effect on the coupling. That meaning, if you shine light at the top of the neuron and you record from the bottom of the neuron at the same time that you're suppressing higher order thalamus, then it's also decoupled. Mm-hmm. And then we found that, so we knew from Murray Sherman's work and several others that the higher order thalamus, when it does project to the cortex, projects both to the top and to the middle of the cortex, and that there's a lot of metabotropic receptor activation involved in about 50% of the work being done by the thalamic inputs is through metabotropic receptors, and so which nobody really knew how to interpret. And we therefore just tried blocking the metabotropic receptors, in this case both glutamate and cholinergic receptors, and both of blocking either of those receptors had the same effect of decoupling the neuron. So information that you were impinging or imposing on the top of the neuron ceased to influence the bottom of the neuron. And I suppose the upshot is that I suppose I should also say that these are the neurons, or one of most, these neurons have a large input to higher order thalamus. And so there's a loop between these neurons, the higher order thalamus, and back again, in controlling the coupling of these neurons. And so if you would break that loop anywhere, what we would claim now is that it's actually taking away cortical feedback, because those things that come to the top of the neuron from other areas of the cortex have no influence, because they get to the top of the neuron but have no influence on the bottom of the neuron from which the axon comes. So basically it's a handy switch, as I was saying in the beginning, for taking away all, in this case ubiquitously across the whole cortex, all feedback. So once you got to that point, then you could posit that that's possibly the mechanism for anesthesia. And our next, I hope we've now got a 5-year plan to see if we can prove that that's true. But on the other hand, we're already speculating that if that is the case, then you could speculate that consciousness is in fact the reintegration of feedback via these neurons somehow, and that engages the thalamocortical loop, or at least I shouldn't say is, but requires, and then you can look at the different kinds of claims about what consciousness is in the major theories, and I think there's basically 3 main genres, maybe 4 main genres. I think Anil Seth, who you interviewed recently, just had a review paper the different categories of consciousness. But one sort is the sort of interconnectivity type theories of consciousness, like the integrated information theory by Tononi, or the global neuronal workspace theory by Changeux and Dehaene. And these are theories that posit that there's long-range interactions going on, and that interconnectivity, in some sense, is the be-all and end-all of consciousness. And you get to a certain level of interaction, which in Tononi's IIT theory would be described by a number with phi. In the global neuronal workspace theory would be some threshold ignition point where you get now, let's say, an explosion of activity around the brain. In this case, I think it's clear that either of those two theories would be well explained, if you like, the mechanism would be well explained as being a decoupling of the pyramidal neurons, because this would instantly take away, either it would instantly lower phi, or it would instantly bring you below the ignition point of the global neuronal workspace theory. Now, another class of theory is the higher order theories of consciousness. Mm-hmm. And in these are more, if I might say, content driven, in the sense that you posit that there's some higher level process going on that is responsible, let's say, exists in cognitive space somehow, that supervenes, if you like, on the rest of the low level activity that's going on. And it would, I think, be easy to posit that's exactly what's embodied in feedback. That if it's going to be embodied anywhere, it's going to be in the kind of information that you generate, as opposed to the kind of information that you're receiving from the rest of the world. Although I think the interesting claim going on here is that it's neither nor. It's in the end, perception or what the cortex is actually doing is comparing to internally generated information with the external information. And it's not until those two things match in the correct way that you have a perception. And I guess if it claims anything, dendritic information theory claims that you perceive nothing when you don't combine these things. And if you would decouple them, you would stop perception, and that would be like being unconscious.
What happened? Okay, so when you're unconscious, they're decoupled. When you're conscious and you have content, they're coupled. What about when you're in a mindful, meditative state?
Oh, nice. Yeah. Or you could ask when you're dreaming or
sure.
And we'd like to know the answer to all of these. So I can only speculate at this point. And I guess the other really close question would be what happens when you take some kind of psychedelic drug and so on.
Right.
And another related question would be what happens in the various kinds of pathologies where you see cognitive changes and so on. I think they all can be, you can think, that's in a sense, the beauty of looking at the cortex through these glasses, that, let's just say, through the dendritic integration theory glasses. You can now say, well, what will happen if you've got basically two dials. You've got what would you say, the receptiveness or the activity state of the top of the neuron and the bottom of the neuron, and you can turn it up or down, let's say. So you've got 4 degrees of freedom, if you like, or two knobs that you can turn in both directions. And you could imagine, for instance, that when you're in a meditative state, that you're turning down your receptiveness to the outside world and turning up your receptiveness to the inside world, that you're basically, or vice versa.
It'd be the opposite, right? And, if mindful, at least mindful, I'm not an expert or anything, but you're turning off your internal world and it's like pure perception, right? Without judgment or without.
Right. Yes. Right. I guess at this point, so I don't know the answer particularly, and we haven't tested the answer, but But I think that's the nice way that simplifies the question enormously. What might turn out is that when, for instance, you're doing something like meditation, that it might be a particular part of you might be switching off your frontal regions and let's say turning down the top on your frontal regions and turning up the bottom on the sensory regions, or who knows. But there could be that kind of nuance to the question. But essentially it's still much simpler question all of a sudden. And it seems tractable to me. First of all, it's tractable because you could describe what you expect really easily. And secondly, it's tractable because we have the tools to explore this now. So with at least in rodents, we can now basically answer the question. We can use various different tools to work out what's going on. In humans, this of course is more difficult, because we can't do the same kinds of sophisticated things like optogenetics and so on in a human. I still feel like there's a path to getting to explaining this in humans. I think it would start with doing this in mostly rodents, but perhaps other animals, and then looking for non-invasive ways to see the clues of what you're seeing in animals, and then take these non-invasive approaches to in the human case. And we've started this in many different ways, and I think it looks promising to me at this point, albeit at the beginning of a long road to get there.
So Matthew, this is kind of a pause or orthogonal, but we've just been talking about high-level concepts like consciousness, and we may go into talk about the ideas about memory and learning in layer 1 and kind of these big ideas. But this all started from recording the nitty-gritty recordings in the dendrites, of pyramidal neurons. So, sort of bottom up, right? And then you've extrapolated to the larger ideas. So I elicited a few guest questions, and I want to make sure that I play them for you. They're both by the same person here. So I'm going to play this question for you with that background that I just said, and then we'll move on to other higher level topics.
Hi Matthew, this is Mac. Nice to see Paul getting a few more Australian accents on the podcast, the way it should be. So one of the things that I really love and admire about your work, Matthew, is your ability to conduct really precise technical experiments at the micro scale, but then extrapolate the importance of those experiments and the outcomes of those experiments to a broader functional interpretation. And as someone who typically starts from the other end at the systems level and tries to peer down into the microcircuits, I'm curious whether you have any tips or tricks for people working on the macro scale that can make the results of our experiments more palatable and more profound to people like yourself who are working down at the microscopic level and trying to extrapolate out to the macroscopic.
It's Mac Shine asking for tips and tricks.
Well, thanks, Mac. Great question. It's so ironic to get that question because I'm normally thinking about the difficulty I'm having talking to people at Mac's level, which I also really admire, and trying to convince them that they should care about the low level features. And I guess Mac is asking the other way around. How would he get somebody at the low level like me to be interested in high level? Actually, that seems to be a theme of your podcast going through. I love the interviews you did with John Krakauer and various people like this who I think are starting more or less where Mac starts, and
they hate the low level, hate it.
Right, they hate the low level. Yes, right. And it's so I find myself defending in the other direction in that context. But if you do want to get through, if you were a John Krakauer of this world and you wanted to interest somebody at the low level, well, I mean, I listened to his argument and I'm totally convinced that you definitely need to imagine what the purpose of all of this is. But I know that a lot of people get lost in the world. In fact, I'm probably in one of those fields where when we get together in our conferences, conferences that are specifically about dendrites tend to focus on such minutiae that if you were a observer to such a conference, you would wonder why anybody would be worried in this, that, or the other. And it gets down to all sorts of details that are hard to know if they should matter at all. And I think it's also true that a significant fraction of the people really don't care about whether or not it matters at these higher levels. I guess that I feel intrinsically if it wouldn't matter at the high levels, I wouldn't care about it at the low level. So I'm not interested in just the properties of dendrites for their own sake. If it doesn't matter at the high level, then I don't think so. But what I guess I'm arguing is that, and this was in an opinion piece that came out recently, I'm arguing that as much as it's important to ask the question, what are the consequences, if you like, at the high level? I think it's instructive. The low level is in fact instructive of the kinds of, it gives you a framework or a parameter to guess what's going on at the high level. So for instance, when we look at the question, well, we recently looked at memory, for instance, and for me, a light came on when I saw that the memory structures tend to go to layer 1 of the cortex. It's one way or another, they feed back information, be it the hippocampus through the medial temporal lobe, or let's say the basal ganglia through higher order thalamic regions, or the amygdala just going directly to layer 1 of the cortex. That for me, that I immediately say to myself, well, there must be a reason for that. And of course, with the kind of goggles that I have on and looking at this in terms of the cortical column and what the pyramidal neurons are doing for that, I'm asking, I'm saying to myself, that must be influencing the top of the pyramidal neuron, and why would this be true, and so on. Out of that pops the hypothesis that drove a whole, 5 years of research, which is maybe the top layer of the cortex cares about memory, if you like, or needs to get signals that things need to be remembered. And if so, it would imply that the thing that you want to remember is context, which actually, the more you think about it, makes perfect sense. In fact, when I was saying this to a psychologist, the psychologist said, we already knew that, that yes, you remember context. That's to say, if I tell you my phone number, you don't remember you don't want to perceive the number 6 any different afterwards if you have a 6 column, or I don't know. You want to associate it with me, and probably a telephone number is the worst example there. But in any case, if you want to remember something, you want to remember the features of something and how they, and what they relate to.
You're now in my tiger context because of the examples that you use, right? So
right, exactly, yes. And so how would I get a high level person to interest the low level person? I would say that this has to manifest, whatever your high level claim is, has to manifest at the low level. And if your low level is if you're steadfastly going to ignore any possibility for this connection, then you will constantly be in your own bubble, as it were, which I think actually a lot of neuroscience is. And it's also, I think there are a lot of exceptions, and a lot of them are, you tend to, I think, collect that kind of a mindset for your podcast. So I can think of notable exceptions of people who really don't stay in their bubble. See, people like Bujaki, for instance, who doesn't want to be trapped in that bubble. But I think being in where I come from at the level we look at the brain, I'm very used to that milieu where it seems really important to talk about, what subtype of what channel is in which oblique dendrite and so on.
Which makes the ilk that you were just describing makes their eyes roll, right? But let me read something. You mentioned the review that you wrote, and it's "Are Dendrites Conceptually Useful?" where you make these kinds of arguments. So I'll just read a quick quote from that because it has to do with what we're talking about. There is every reason to suspect that better descriptions of sophisticated single-cell computation will lead to better descriptions at the network level, blurring the distinction between Mars algorithmic and implementation levels. So people, you mentioned John Krakauer, he's one example, right, who don't care about the single neuron level, let alone dendrites, right? That's even worse. Because the argument is we have to stop looking at how these neurons are connected as like box and arrow kinds of diagrams, because they're not telling us anything about the higher level cognitive functions, essentially. Are you fighting an uphill battle in this current, not amongst your low-level dendrite friends, low-level friends, but just in the neuroscience world at large? Have you found yourself fighting an uphill battle as a sort of bottom-up experimentalist?
Yes, I think it's always very difficult to take somebody who hasn't considered these problems and even get them to pay attention, let alone take it seriously. And I guess the claim I'm making in the quote that you just read is that it's not just the claim that there has to be a through line from the implementation to the algorithm to the computation, but that the implementation is very suggestive of what types of algorithms and eventually what types of computations are being carried out. And that sounds like an unreasonable claim. I'm sure to the John Krakauers of this world that doesn't seem plausible, but I think that what we've just been going over is a case in point. I think there are things that we're suggesting, such as, for instance, perhaps the top of the cortex is the place where you should look for semantic memory, that you can only come to by a synthesis of this bottom-up approach with an eye to the top-down types of questions. And in the end, it, I think, is really instructive to somebody from a psychological point of view and somebody who wants to understand, let's say, computation level in Mars terminology.
Right.
But in terms of getting back to looking at high level features of cognitive features of the way the brain operates, it not only, I think, suggests how it operates, but why it operates that way. It makes a lot of sense, I think, that if you want to remember the way things are associated or the context for things, then you would like to separate that. It'd be really useful if you could separate that as a compartment, to handle it separately, and then reintegrate it into the larger cognitive domain. And hey presto, that's what the low level is telling you is happening. And all of a sudden it's giving you clues about how you should talk about at the high level about what's going on. And it also tells you why this is semantic information, by the way. This is essentially semantic. It is a really difficult notion, meaning or how do we describe this? In the end, it tells you if this is the right way to look at it, then semantic means nothing other than the distillation of context. And so if you can distill the context of something, then you know the meaning of it. And yes, that's a bold thing to claim, but I'm claiming it on the basis of the low level description. And I'm saying that it appears that way from the low level description. So let's posit it as a hypothesis at the high level.
Well, so I guess a pro computation level perspective would say, that's fine, but you didn't start with dendrites. You actually had memory in mind, a high level concept, right? A computation in mind to then make a hypothesis about what the dendrites might be doing. So to me, it seems silly to say we need to go this way or that way because we're all working at all levels. It's essentially not me since I'm retired, but.
I couldn't agree more. That's exactly right. That it should not be a fight between which direction to think of things. There should be a call to arms for people at all levels to start talking to each other and to see how this all fits together. And I think that's what I admire a lot in Max Schein's work, because he's doing that. And there are very, very few people who do that, and a lot of people who are resisting it.
Since I mentioned that paper and read a quote, are dendrites conceptually useful? How's it been received? Have you gotten feedback, positive or negative? Did it do its job?
It's too early to say now. It's only a few weeks since it came out. I've not had any really negative feedback, but maybe it's still arriving in the. I do kind of feel I'm a little bit conflicted by this paper because it's a little bit polemic, at least for what I'm used to saying. I'm usually a little bit more tentative about saying it, but what it's trying to say essentially that there may be things that we've yet to understand about the way the brain operates that can only be approached if we would include some of the possibilities that we could learn from dendrites. And the analogy I have actually, which is in this paper, I look at the way I contrast the revolution in neural nets with a normal digital computer. And I think it's fair to say that neural networks are conceptually in advance for neuroscience. Mm-hmm. No matter whether you think they're the be-all and end-all, but certainly deep neural networks are doing a lot of work at the moment in terms of our understanding of how networks might work. And I think this is on a conceptual level. And I think it's on a conceptual level in the sense that we run these artificial neural networks on digital computers, which are nothing other than Turing machines. So you could, because maybe I should add that often the throwback that you get as a dendritic researcher is, well, you know that it's not really necessary to consider these dendrites as for neural networks, because we can always build a more complex neural network that includes all the properties of your dendrites. And so it's not relevant, is it? And we'll be able to solve everything with point neurons, because if we needed something that the dendrites do, we'd add a few new point neurons.
New points. Yep.
Yes, right. And I'm just saying, well, you could have said that about neural networks in the first place. You could have said, look, I don't need a neural network to solve this, because all I need is a few more states and a longer ticker tape to have more numbers on it. See, it's just a Turing machine after all, and I can prove it because I can run it on this digital computer. And you'd have, in that instant, lost all of the power of having collapsed what I think is the real insight of a neural network is that you can do this fantastic statistical learning with basically three facts. If you have a learning rule and you know the cost function of this and you have basically a particular architecture of you've figured out your connectivity, that with those, armed with those facts, you can a method for communicating the deviation from the goal that you want to all of the connections, you're done. And you can beat the world's best chess player with these three principles, essentially, with a few tweaks. And so obviously I think that's a conceptual advance, and for me, it's absolutely not an argument against this that you can run it on a digital computer. I'm saying, so what? That it's conceptual advance. So the argument would be, we haven't spent enough time looking at the kinds of insights you might have over and above these things we now know about, or this framework of looking at learning with a neural network. We haven't looked at dendrites closely enough to know whether or not there are more principles on those levels. And the first principle I would go for actually is the separation and reintegration of two different fundamental streams of categorically different streams of information, and mess around with those kinds of principles. But I'm not claiming that is the be all and end all. I'm just saying that seems useful intuitively to me at the moment. And you'd want to be really sure before you just threw away what biology has spent hundreds of millions of years playing around with, and just say, well, that's irrelevant. I think I'll stick with point neurons. That seems to me to be an incredibly stupid thing to do.
Yeah, okay, I like that you said stupid. I recently had Elena Galea on talking about astrocytes, for example, right?
Yes.
Thinking about things that are not neurons in the brain. Of course, there are neuromodulators, and I've had people on to discuss those. But it just seems, the more I think about it, the more I learn about some of the lower level things that were carved through evolution. the sillier it seems that the deep learning world is based on these point neurons, right? That are essentially from the 50s, 40s, and earlier is by looking at the brain and deciding that neurons from the single neuron doctrine, et cetera, were the end all. That's where artificial intelligence, or the modern version of it, the birth of deep learning, et cetera, that's where it all started. And it just seems silly that it's so archaic, based on the technology that we had at the time and our experimental capabilities based on those technologies. So I'm with you that it seems useful to at least try out what evolution has suggested to us.
Right. So I guess I want to just reiterate the claim that I'm making. It's not that I imagine in the end that you're going to need a sophisticated, real description of dendrites,
right.
And that unless you had a really complex machine with dendrites, you wouldn't get the full functioning brain. I'm claiming that there are insights that you can get from dendrites, and until you understood what they're really doing, then you'll miss these insights. In the same way that if all you had was a finite state machine and a ticker tape, you're probably never going to stumble across the idea of a neural network. You'll probably, if you only have neural networks with point neurons, you're probably not going to stumble across some of the insights that you can see with these higher concepts, whatever they may be. And I guess to the John Krakauers of this world, I would say, just that's an example of, let's say, that's where I'm trying to say we may be confusing implementation with algorithmic. I'm not quite sure how I would describe the point neural network in terms of where it fits on the Mars level of description. But I think it's clear that it blurs that description, because you can get from a neural network now to beating a chess player and all the other face recognition and God knows what will come around the corner next. That there are insights that we're getting from that are crossing these boundaries, as Ma would put them. They're not so simple to see the line between what. In fact, in a way, this is perhaps more the problem that we're facing, because when you sit down and, when you want to beat the world's best chess player and you want to improve your network, now comes the rub, actually, because you can train it on 100 million chess games and it's going to be fantastic. But if you want to improve it past that, you suddenly realize you don't understand how this neural network in front of you is solving the problem, or at least in the sense that you don't understand it, in the sense that you don't know how to tweak it to improve it past giving it more information and training it more. But I think that's where dendrites are likely to come in and be useful, because clearly what I think, this is a hypothesis or a wild claim, if you like, that neural networks, point neural networks, deep neural networks are autistic savants. These are machines that can collect information and synthesize that close to perfectly, such that you get close to the best statistical description of the input-output function that you're seeking. And in that sense, you can't do better. And what you're missing is context. What you're missing is a way to, when we're talking about sort of general AI, that you're missing insights in a directed way that allows you to do what is difficult for autistic savants, to put some meaning to it all. So you might be able to count how many matchsticks fell on the floor, but you've no idea what you're going to do with this information. And you can't put it in other contexts that you haven't been trained to do, and so on. And what we clearly can do with one or two presentations of the data, humans in particular, but I think mammals in general, can generalize from situations and make conclusions that are startling with comparison. So and at the moment we're all super impressed by something that is, as we would be, I think, if you meet an autistic savant, then you're also super impressed by what they can do. And I think your first impression is, I wish I could do that. But I think I think it comes at a cost, and I think the low-level implementation is telling you why it comes at a cost. It's because let's say that you could train this whole network in a feed-forward sense by just using the bottom of every neuron. And now you would be putatively perfect or at least as good as possible in framing problems. But if you want to have context, it comes to the other end of the neuron and is reintegrated into the neuron. There's only one output from the neuron. So essentially the top-down signal is adulterating your perfect statistical calculation. And you can't have it both. You can't be perfect in your statistical analysis of something and have your context at the same time. And so you're going to have to put up with that. And my claim would be that from an evolutionary point of view, you want to be something like the six-layered cortex and a mammal that is imperfect, because from an evolutionary point of view, every now and again you're going to come across life-threatening situations where you're going to have to think laterally and use all your knowledge to avoid it. And I think we come across them actually not just every now and again, but all the time, particularly say you're driving a car and today somebody dropped their hat in the road or there's some strange obstacle in front of you. And let's say an automatically driving car would just say, well, that's the first time I've seen that. I'll add that to my database and run over the little kid or whatever it is. And you say, no, this is strange. I've not seen this before and I don't know how to handle it, but I can see that something's different. And I know I can work out all of a sudden that all of these other things pertain to the problem. And although you've not seen it before, you can deal with that. I should have framed this in terms of the driver dying. You could easily frame this in terms of and
children. You're talking about children dying. Nice.
Oh, sorry about that. But my main point is that you would be coming across situations throughout life where if you didn't have this kind of ability to think on your feet and interpret it, you're going to die. And let's suppose I told you that this autonomous vehicle was so good that in 10 years of driving, it'll be 100 times better than you are at driving the car. But once in 10 years, it'll drive into a truck. You don't get into that car because you're going to die in the next 10 years, and you don't want to die in the next 10 years. You want to survive it, even if that means making hundreds of little errors that are not optimal. You would prefer to be ready for the divergence that is hard to predict and you can't learn statistically. So that's what I'm guessing is the reason why you need this kind of general intelligence from an evolutionary point of view.
I had the thought, and you can tell me why this is a ridiculous thought, but thinking about our mammalian cortex and our human cortex relative to other mammals, it is thicker, and these their descriptions of these layer 5 pyramidal neurons, for example, have longer apical dendrites. They're more decoupled, essentially. And I was trying to think, under your like the dendrite hypothesis, why would that be? And I actually thought maybe one evolutionary advantage, and sorry, you talking about the savant made me think of this, is to actually prevent us from, you said it for me, from like being a savant. It's actually to prevent us from learning too well, so that we have the capacity in those situations over a mouse, let's say, or in this case, a savant. I guess I'm just repeating what you said, but I thought of it in terms of reducing what we're learning in given situations, even though we have a much higher, to allow us to have a higher capacity to learn when we need to learn. Does that make sense?
Yeah, I really like that. I hadn't actually thought of that, but that's really nice. So in other words, the thickness of the human cortex would have a tendency to be able to be savant-like because it's more decoupled, is what you're saying.
Well, the thickness would prevent savantness, right? It would, because you wouldn't just learn everything without the imperfection, without the feedback, right? The feedback in some sense is gating your ability to become a savant, is what you said. Right. But now I'm just, it was just
that's right. It's what the reason I extrapolated to that from what you said was that The thing, actually, the first findings in vitro from human neurons is that they're less coupled than the rodent neurons, and that which seems counterintuitive at first. And
that's what I'm saying. Is like to prevent the learning, essentially.
Right, but then you would need some way to reintegrate that. So, and I think that I'm betting that the latest thing that we saw under anesthesia is giving us the answer here. That essentially different kinds of neuromodulation affect the coupling. And I'm betting that if you took a human neuron in a situation that's more sophisticated than the in vitro situation where there's no neuromodulation, that you've got all sorts of ways to reintegrate the tuft. And as you say now, you could be doing learning with and without it. And I suppose that I guess where I was going was saying that also, first time, I didn't realize you weren't saying it now, so we can own this idea together, that you would also, in principle, have the advantage of being able to decouple it under certain situations. So right. If you just wanted the statistical part of this, if you just wanted to, let's say, ram a lot of information in, and you could, in principle, I don't know exactly whether it happens or how you would do it, but in principle, if you've got a mechanism to decouple the top from the bottom, and you were under control of that, you could, for whatever time it takes, decouple it. And maybe that is what it means to really focus on throwing a football or something.
Maybe that's what Ritalin does or something. Yeah.
Right, exactly. And then you could putatively work up the statistical information and then reintegrate the context. I guess that the way we had thought that this happens is in two stages. But it's just at this point we're, I guess, so this is really speculative, but one way you could imagine is what the critical period is during the development of a mammal.
Right.
Is a period where you are decoupled. By the way, at least in a rodent, during the days between, so when you're born up until just after weaning, that's a few weeks, so 3 or 4 weeks, you don't have a calcium spike and you don't have this apical non-linearity. And then it starts to kick in at around about 4 weeks and then up to about 8 to 12 weeks, it's really fully developing, and then you have really large plateau potentials. But so you could, and that corresponds to an early phase where there's a critical window where you're learning just the features of your environment,
the statistical regularities.
Right, and you basically shut down the top of the neurons while you learn the statistical regularities. Now you've got the features in place in your cortex, and you're grounded in the world, and all your columns are grounded. And now you can start putting them together, associating them to each other. And I guess that I was positing that that's when the critical window ends and you stop being so good at learning statistical. And that would explain, for instance, why it's difficult to learn a new accent.
Or instrument.
Yes, or instrument. If you haven't got that grounding with the world up to that point, that gets slowed down deliberately because now you don't want to be bothered with that. But as I say, why not have maybe you need Ritalin and you prevent feedback or something. You could, in any case, you could imagine that again, this is a handy conceptual tool for trying to understand the link between the implementation and these large scale concepts of in this case, learning statistical information versus contextual information. So whichever way you look at it, I think so it might be wrong, but if it's wrong, at least you've got a framework for talking about it and testing it. Mm-hmm. And for me, that's worth something. that gives you a way to treat this, what otherwise seems like an intractable mess of possibilities. So
I've heard you, in your talks, and this is going back to artificial neural networks now, talk about how we don't need to model dendrites, and you've just been talking about that as well. We don't need to model all the exact details of dendrites to create a useful artificial intelligence, for instance. That instead we can extract the correct principles that the dendrites, just like we've been talking about. How much detail do you need to build in it? Are there lower level things that you think are dendrites the lowest level that we need to consider, or are there principles that we can extract looking at lower level things like, I don't know, channels, right? Ion channels, or whatever. I don't want to plant a seed in your head, but are dendrites the bottom level?
I don't know the answer, and I mean when we're talking specifically about dendrites, there's levels also in dendrites. So you could be talking about spine heads or the little branches or whole arborization, and so on. And it's this is a well-known thing. Actually, I don't know if you've talked with Mike Heuser before, but he and Bartlett Mell have a really good paper. It's now about 2 decades old, asking exactly this question, whether or not what level is appropriate. And it wasn't clear then. I don't think it's clear now. And I mean, I've got my favorite intuitions, but I don't think you're asking that. I think the larger question is, how would you know, and what's the principle for deriving this? And
you have to take a walk with your wife, and it has to come to you in a flash.
Exactly. No, well, yes. Actually, if there's one principle to come out of that, you need a really naive person to say, well, wait a minute, and not to stop asking you, to keep on coming back to something you thought was obvious, and keep on having to explain why you think it's obvious. And actually, my experience is trying to explain to somebody, a really persistent, naive person, why something is obvious.
So marry a naive person is what you're saying.
Something like that. But actually, I think in the end, that's why I think teaching is actually really useful too to students, because often they're asking you naive questions, and then you find yourself, actually, I don't really know the answer. I thought I knew the answer to that, but actually, and very often you realize that even the student doesn't realize what they're asking. It's not necessary that the naive person has the insight that you're having in that moment for you to suddenly realize that you don't really understand that. And I wouldn't claim that anything that I've said now is categorically true. It seems, the good news, I think, is that if you start with this mindset that there's something to be learnt from, let's say, bottom-up descriptions, that then you can always test it. Well, you can mostly test it. You've always got at least a conceptual way to test something. And that's worth gold dust, I think, in a scientific context. Because if you're starting from the really high level ones, you may or may not be able to test a high level theory, particularly if you are on the wrong track, then it's going to be very difficult to get any proof at all. It'd be hard to get in there and actually test it. I think that's worth a lot. But the bad news is that it's hard to stumble across the high level concepts that way. And so that's why I think you were right before. Everyone should be talking to each other, and we shouldn't be doing one or the other.
Okay, Matthew, speaking of naivete and relying on our assumptions and questioning our assumptions, let's get to the action potential and consciousness thought experiment piece. Do action potentials cause consciousness? This really challenges our assumptions about what's important and the primacy, again, of action potentials and, I guess, somatocentric thinking in a sense. Would you like to explain the thought experiment and maybe high level? Sure. And then I have a question from Mac Shine, and then we can discuss more.
Just before the caveat on the description of this is that
that you hate neurons, you hate cell bodies and action potentials.
Well, first of all, the question, as stated, as you put it, is supposed to be provocative.
Yes.
And so to be even more provocative, I think I would say, does brain activity cause consciousness? And I guess I would be hoping that my interlocutor, like you, would have the spontaneous response, of course. So that's what, in a sense, that thank you, that's where the starting point should be. But because then the thought experiment starts, and I should first of all say that this was put forward in our philosophy club in our lab by a really fabulous now senior postdoc, Albert Giddon, who proposed this one day, and it sounded so similar to what I'd heard in other kinds of contexts, that at first I thought that it wasn't new, but there's something really important about it. And more recently I found that there are a few other people who've either said similar things or the same things even. But here it is. So imagine that first of all, you take a subject and you give them some experience. So I think it's easier to do this with, let's say, a movie. So you get them to watch 5 minutes of a movie. And while they do this, you use some modern technology, where you record from every neuron in the brain.
So future technology.
Some future technology. Right. What we'd like to, if you go to some conferences, what you'd like to believe we're closing in on, but probably we're still a long, long way from. In any case, so you record from every neuron. So you know how every neuron fired during the movie at every instant. And you can, just for the sake of this thought experiment, record from the retinal neurons and also any neurons in your spinal cord and so on, so that, the whole deal. But in principle, we're talking about what you were thinking when you saw the movie and the experience you had when you saw the movie. Okay. And now you imagine that you had a device to replay that to the person. And actually, although to some people, this sounds really, really futuristic, and that's not futuristic. Futuristic is the number of neurons you can do at the same time.
Right.
But getting one neuron to repeat the exact activity in the form of action potentials is not even hard. That all you need is a really good amplifier and a good recording of the initial conditions, and you can do what's called dynamic clamp on the neuron and literally create the same voltage at that point where the neuron is, which is unfortunately, as I say, typically at the cell body, but nevertheless, you can make the cell body do exactly what it did before. And since that is actually a nexus point, because most of the dendrites are feeding into that point, and that's just before the axon, that's going to have a pretty that's going to really dictate what the output along the axon is of that neuron, if you can absolutely recreate. And not only that, but if you do a dynamic clamp in a continuous way over the whole period of this movie, it won't just dictate what that cell body should do when it fires an action potential, but every other part, so every subthreshold deviation from that as well. So in other words, the cumulative effect of all the inputs as seen at the cell body, you can recreate with this so-called dynamic clamp. And now, okay, it's futuristic, but let's say you now do this at every neuron in the brain. The question is, if having just seen a movie and somebody recorded all your action potentials, if they replayed all the action potentials very faithfully at every neuron in your brain, would you have the experience of seeing the movie again?
And
can I challenge you with that?
Well, because I've kind of vacillated. So, I want to say sort of, because I don't, it's not to me, there are questions, right? Because, well, I've ended up on no, but I think that it's because, I've come to think of, let's say, our subjective experience as not being due solely to spiking activity. So I was already kind of a no on this, but I definitely would have said yes.
Okay.
Very pro spiking.
Okay, let's just take your used to persona, because there's a couple more steps. So if you would say yes, of course.
Wait. Well, what would you say?
I would say what you just said. Actually, I'm agnostic, and I think I would jump off the train at the very first step and say no. But I'm very conflicted. I don't know the answer. And For me, this is torturous. But the next, I think a lot of people would say, of course, Penfield used to stimulate the brain and you had experiences. So if you made the neurons fire, you just had the experience that gives you. And really important to this thought experiment is that although we're not controlling everything else that's going on, including the glial cells and the neurotransmitter and so on and so forth, but we're not interfering with it either. So there's no reason not to posit that when the action potential goes down the axon, it won't lead to the same release of transmitter and so on at the other end. Of course, that's a stochastic thing, and maybe that's important and so on.
Yeah, that's a homeostasis and all sorts of things. Yeah.
But on the other hand, if let's suppose homeostasis was coming in, at every subsequent instant in this, you're also making the neurons do what they're going to do. So you're never going to know what homeostatic changes actually occurred.
Yeah, I meant in the astrocytes and glial and all the other parts of the brain, yes. Right?
Right. Okay, I concede that. If you wanted, you could extrapolate this thought experiment to clamping everything, but this seems too unnatural for the timing. So let's just stay where we are.
Next step again, and then because I need to play this before you answer it already.
Okay, all right. So the next step is what would happen if you now blocked all the sodium channels. So you blocked all the chance for the action potentials to propagate down axons, but nevertheless, you make every neuron fire the way it was doing. So if you got to this point, I think you should be saying something like, well, it didn't matter before whether or not the action potential influenced the next neuron because my electrode is telling the next neuron what to do, not the action potential from the previous neurons. So in principle, those connections are now, the action potentials that are going down the axons are irrelevant because what makes an action potential is no longer the influence from the, so then but nevertheless you would ask, would that cause you to be unconscious? And then the next step would be blocking neurotransmitter, and so you could put in, let's say, drugs that blocked the receptors, or we did it in a sophisticated way in the thought experiment with the optogenetics and so on, just so that you could get around some of the tricky problems. Yeah. Well, it's not so much that it's believable. Actually, it gets a little bit more fantastic that way. But mm-hmm. I think it avoided some of the obvious complaints somebody might have on a sort of philosophical level. Let's say could do it more cleanly. Let's say than just cut out just transmission. And then the next step in the argument is, what if you take each of the neurons? Well, first of all, what if you make an incision in the brain and you cut one part of the brain from another, but you're still clamping every neuron? So essentially, the information is getting around the brain in the sense that you're imposing it just like it would have happened in the original brain, but they're physically not connected anymore. But they weren't connected anyway due to your blocking of neurotransmission. So why should that matter? And then the last step is to take every neuron in the brain to a petri dish, spread it around the world, have different researchers in there, different laboratories replay at their neuron what they had to do, and then some set of neurons that used to be your brain does exactly what it did before. And I think by most people at this point are starting to object. They can't imagine that would be conscious.
Not panpsychists, though, probably, right?
Right. And so and then you ask yourself, well, if you decided that at some point in this set of steps, you went from being conscious to unconscious, you have to say where and why. Yeah. And, so that's where we get to. And then that's very challenging, I think, because now you have to have a more, first of all, you have to have some better reason for explanation, or let's say imagination for what would make you conscious. But also, and this is where I think it's an important thought experiment, is that whereas, say, the Chinese room does something like this, and various other ways of looking at what computation does, and different ways to simulate what the brain does are good thought experiments. Very often, and actually John Searle, the originator of the Chinese argument, I think does this. When challenged, he says, well, I know I'm conscious, so there must be something about wetware that makes you conscious. Mm-hmm. And it's like the last retreat. I don't know why I'm conscious, but I know that I am conscious, and I know that I'm a set of neurons. So it must be something special about a set of neurons. And basically this is saying you can't escape, because it's still your neurons doing this. In fact, in the most idealistic way of stating this, you're in the first step, when you replay all this activity, you can posit that all your neurons did exactly what they did before, and that and if you want to say, well, no, they didn't, there's this there or this there, you have to now say why that should be the seat of consciousness. So I think I'm just saying that you can no longer retreat to saying, well, there's something special about the way you framed this and actually, but I still retreat to, yes, brain activity causes consciousness.
Right.
Because you're being asked, why does brain activity cause consciousness? And
that's what I was going to say, is the frustrating part of this, because I feel comfortable, I guess, like you, jumping off at the beginning, but then I cannot articulate why, right? So, which is the important part. What else then? Yeah. Why would it be? Yeah. Et cetera.
Right.
Okay, I'm going to play this question from Mac, and I'm not sure whether you want to answer or what you'll think of it. So, all right, okay. Here, I'll play it.
Hi, Matthew. This is Mac. You, Albert, and Jan recently had a quite thought-provoking thought experiment. And in the spirit of playfully manipulating thought experiments, I wonder if you have thought about some of the other aspects of this thought experiment. And I was imagining a situation, as someone who doesn't do a lot of cellular neuroscience myself, that some of the patch clamping could go awry. And I started wondering just how much of that patch clamping could become impaired or could be inaccurate for an individual to have that same conscious experience. In other words, how robust do you think our conscious awareness of an individual moment is to individual variation in the firing or the activity patterns, the calcium dynamics of the cells distributed around our brain?
Okay.
Oh, thanks, Mac. Yeah, I love that question. And I think I don't know if you were being triggered by that, but that was sort of what you were just alluding to before. I think that the actual potential that causes release is a very stochastic process. And so that's one form of things you're not under control of in this thought experiment. But I think I like the question because it's framing something in a way that I've been sort of playing around with. I love to listen to Dan Dennett and his kind of theories of consciousness that, by and large, I find myself agreeing with him in a sort of matter-of-fact way. But he also talks about free will, and that's another thing that I'd never linked free will and consciousness in particular before, but I start to see that there's some link between these two topics. And you know that there's famously, there are lots of neuroscientists who think free will doesn't exist, but nevertheless you're conscious. And one thing in particular that struck me about, something that Dan Dennett talks about, and I think he's actually talking, I forget the originator, is it John Aston or somebody else was talking about, it's the putt example where a putter comes to the green, he's with his colleague, he tries to putt the ball into the hole. He says, damn, I could have got that, when he misses the putt. And then there's this big philosophical, article about what do you mean by you could have got that? And do you mean that if every particle in the universe was exactly like it was before, that you could have got it on one reversal of time and not on the next reversal of time? Which is effectively the same as saying, can you break the causal chain of the universe? And if you can't, then maybe you don't have free will. And I think the same thing could apply to, that's one way of framing what consciousness is about, that essentially and it comes back, I think, to maybe to the Dendrite theory, because essentially one way of framing what's going on with the architecture of the cortex is that in order to have any perception, you don't just receive information from the outside world. In fact, almost to a large approximation, it's the other way around. You make a guess about what the outside world is telling you. and you compare this to what the outside world actually tells you. And it's in that interaction that you have perception, that you have a sensation, let's say. And given that the neurons that are going to eventually represent this also project all the way down through your sensory space. They also go all the way, in some cases, all the way back to your sensory organs. Certainly in hearing, for instance, you're actually using your cortex in some way to modify the outer hair cells and the game of your ears and so on, and you're affecting the input and so on. So you could imagine that sensation that you're having of hearing and why it's different to vision is exactly because of the question that you pose to the distal parts of your dendrites, where you say, is this the case? Do I get what I expect in this situation? And if you're expecting something auditory, you actually not only have to expect an auditory type of sensation or effect in the feed-forward direction, but you have to, your expectation will become output that will interfere with the whole loop of information coming from your ears and so on. So that's a first pass way to explain why this view of the cortex encompasses why seeing red is different to hearing the middle C on the piano, say. And now getting back to the variability, of course, this has to be, for you to perceive in this framework, it has to be that there's some way that you could be wrong, let's say, it's in the deviation from what you expect that you actually make the important perception that the extent to which this is or isn't what you expected is the extent to which you assess what you perceive and the extent to which in the end you have an experience. So the experience is all in the noise, if you like, in this sense. Not in the noise so much as in stochasticity, but in the noise as in the deviation from expectation. And so that would be a way. I don't feel confident enough to claim that. Now, I'm not a philosopher, so I suppose I should farm that one out to people who are more experienced than I am. But I say this for two reasons. One being this thought experiment, and the other, this framework the goggles that I have for seeing the cortex, that's maybe an escape route that you can frame all conscious experience in terms of this interface, which might actually be at in a sort of meta space, let's say, not in the nuts and bolts of what action potential is fired and so on, but in if this higher order, what should I call it? If this, I'll say it, higher order, question that you're asking of an ensemble of columns around the brain has meaning. It has meaning because, first of all, you're grounded in the world, and you're asking questions of grounded columns. And second of all, because it can be that it doesn't have to be the case, and you're asking this question. And so in a world where everything is just a repeat, you will never see any deviation or never have any, so everything will be your simulation, and therefore it won't be an experience anymore. And if it's not an experience, you won't be conscious of it. So that's
fantastic.
But
yeah.
Maybe I kind of feel like a philosopher will catch me out somewhere in that loop. But it feels. I guess I'm positing it. I get to. So this actually is a nice way to close the loop, because you're asking, how do I convince the John Krakauers to see from the bottom up? Mm. I'm saying that I'm asking a really now high level question, probably one that's probably more high level than he wants to go for, but I'm nevertheless looking at the implementation that I see and asking, well, is it at least plausible at the implementation level, given this broader perspective of why the implementation is the way it is? And I at least get a loop that's closable. I agree that one needs to look at this closer, but But I say I came to this with some inspiration from the implementation level. And B, I claim that if ever I'm on the right track, I've got some things to test here that is also, from my point of view, this is an important statement to be able to make, that this isn't just, so I might well be wrong, but at least I've got the way to check it, or at least theoretical ways to check it. There's the conceptual ways to check it, let's say. Let's hope that we get the appropriate devices going forward soon.
Well, Matthew, it's time for us to close our loop. And this is a long episode, and I still had plenty of things to ask you, but I appreciate you letting me put your goggles on for a little while. And I've really enjoyed reading all your works and continued success. I know that you have a ton of experiments left ahead of you, a lot of ideas to test, and it's in some sense only the beginning, right? Yes.
Well, I guess it's never ending.
Never ending.
But I mean, it's such fun that's probably a good thing, not a bad thing.
Right.
So yeah, we're looking forward to the next 5 years.
Oh yeah, you have your 5-year plan. All right. Thank you, Matthew.
No, thank you. It's been great.
Brain Inspired is a production of me and you. I don't do advertisements. You can support the show through Patreon for a trifling amount and get access to the full versions of all the episodes, plus bonus episodes that focus more on the cultural side but still have science. Go to braininspired.co and find the red Patreon button there. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thank you for your support. See you next time.